The next topic that we are going to discuss is the detection of a signal in the presence of additive white Gaussian noise. Now, what do we mean by that? By additive white Gaussian noise? We'll discuss that shortly. But let us first look what happens when we transmit a signal which has been represented by some kind of a line code. For example, we took an analog signal, converted it to a stream of bits. Okay, we have a stream of bits here, and those bits have been mapped onto some analog waveform in the form of pulses. Here I have used a unipolar non-return to zero line code to represent these bits. So basically these are pulses, or the kind of pulses that we would obtain at the end of the analog to digital conversion process in a PCM system, for example, right? So we have this black waveform. The rectangular waveform is nothing but the voltage levels representing the ones and zeros, and we are considering the binary case here. So we have only two voltage levels, which is plus A volt representing a binary 1 and 0 volt representing a binary 0. And because we have only a positive voltage and a 0 volt, so it's a unipolar waveform, and we don't have any zero crossing in the middle of the bit interval, so that entire duration is the bit interval. So therefore it is a non-return to zero, so it's NRZ unipolar line code. Okay, so that's our signal that we are going to transmit. For example, here I'm not yet beginning to discuss about modulation. Okay, we are talking about transmitting the baseband signal as it is without modulation. If we happen to do that, okay, although we generally don't do that in practice, if we happen to transmit a baseband waveform over a communication channel which adds some noise, what happens to the received signal? Okay, that's what we are interested in seeing here. So this black rectangular pulses that you see here, that is the transmitted signal, which we are going to denote by the letter small x. It's a function of time, so we can write it as x of t, but nonetheless I'll just call it as x for simplicity of notation. So the transmitted signal, which is this black waveform, is denoted by the letter x, and then the red waveform is what we are going to receive at the receiver side. And what we notice here is that the red waveform, the received waveform, is not exactly as the transmitted waveform. It is having some random fluctuations around the voltage level corresponding to the transmitted waveform. So that random fluctuation comes because of the noise on the channel. So we have the channel adds some noise signal to whatever we transmit. So the transmitted A volt together with this noise component gets added, and we get a random variation of the received voltage level around the transmitted voltage level. Okay, so the received waveform is represented in red here, and we denote it by the letter Y. And then at the bottom here we have the noise waveform, which gets added to the transmitted signal as the transmitted signal propagates through the communication channel. So the noise waveform, as you see, is a random waveform. So noise is a random signal. Okay, but we will find out some properties of this random signal using some concepts of probability. Okay, so the topic of discussion for this particular lecture is to know what is the effect of noise on the transmitted signal, and what is the relationship between the transmitted signal X, the received signal Y, and the noise signal N, when we say that the communication channel is additive white Gaussian noise channel, AWGN channel. Okay, we want to establish what is that relationship, and we will focus more today or in this video on the properties of the noise itself. So we are going to discuss in particular what do we mean by additive, what do we mean by white, and what do we mean by Gaussian. These are the three attributes of the noise that we are dealing with in this particular course. So we will I will elaborate what do these terms mean in the context of this course. Okay, right, let's first write down the relationship between the transmitted signal, the received signal, and the noise signal. So we have denoted the received signal as Y, and that is equal to the transmitted signal X plus the noise signal N. So the relationship is Y equals X plus N. So the received signal is the sum of the transmitted signal and the noise signal. Okay. So that brings us to the first attribute of the noisy channel that we are discussing here, which is this additive, right? So by additive, we mean that the noise gets added to the transmitted signal. So if you see here, it's getting added. So we call it as additive noise. So it's the effect of the noise is not multiplicative or convolutive. So there are many other operations effects that can happen, but one of the most common types of communication channels is the additive noise channel, where the noise gets added to the transmitted signal. So by additive, we mean that the noise only gets added. There's no multiplicative or convolutive effects or any other effect for that matter. So that's the meaning of additive. Then we want to talk about what we mean by white, the second attribute, which is white. So we have this white here. What do we mean by white noise? Now, by white noise, we mean that the noise contains all frequency components in equal proportion. So noise contains all frequency components in equal proportion. Now, what do we mean by that? For example, if we had to plot the spectrum of the noise signal, so we have the time domain representation of noise at the bottom here in the blue waveform. If we had to take if we take the Fourier transform of this noise signal and plot its spectrum, or rather, we will square that spectrum and make it as the power spectrum. Okay, then what we will see is that the excuse me, just one moment. So if you plot the power spectrum of the noise signal, we are going to get a constant. That means the power spectrum is going to be flat like this. So let me use a different color and thickness. So okay, so the power spectrum of noise, more specifically we call it as the power spectral density of noise. And if you notice, it is flat in the sense that it has equal proportion of at all frequency components. So whether the frequency is 0 Hz or 10 Hz or 50 Hz or 1 kilohertz or 10 kilohertz, the power contributed by the noise, the power of the noise at that frequency is the same. So the power of the noise at all these frequencies is the same. So the effect of that is such that whether we transmit at this frequency or at a different frequency or at an even higher frequency, wherever in the frequency band that we transmit, we will have to deal with the noise, because there will be an equal proportion of noise at all frequency components. So that's the meaning of white. Okay, you can take this, for example, if we have a red color or a blue color, each color is represented by a specific wavelength and hence a specific frequency. White, or pure white in the physics sense, is an equal mixture of all the colors. You take all the possible colors and mix them in equal proportion. That gives us pure white. So white means it contains an equal quantity of all the frequencies or wavelengths. So that is what we mean by white. And the noise that we are going to deal with is white noise, in the sense that it has an equal mixture of all the frequency components and hence all the wavelength components, right? But if we were talking about a specific color, then red has a specific frequency and specific wavelength. Yellow would have a specific frequency and wavelength, and so on. But white means it has all frequency components in equal proportion. So irrespective of whether we transmit at a lower frequency or at a higher frequency, whatever is the frequency band we use for communication, we will have to deal with the white noise. So that is the implication of the noise being white. Just to illustrate this further, let me give you another example of a channel which is not white. So what we have plotted here is the power spectral density of noise. Okay, we call it as the power spectral density. And we would normally represent that as Gn of f. Okay, it's a function of frequency, and we see that at all frequencies the value is the same. So the spectrum of white noise is flat. Now let's suppose we had a communication channel where the noise is not white. For example, suppose we had a channel which had its power spectral density looking something like this. So it's flat to this band, and here in this band it is having less noise, and so on. Okay, again that's the zero frequency, and the spectrum is symmetric for real signals, right? So if you notice this particular channel, and if this is the power spectral density of noise, that obviously it is not white noise anymore, then what we notice is from a frequency of say 0 Hertz up to this point, the noise is having a certain value. Okay, so I'm just going to mark these off. But in this band, in this particular band over here, we notice that the noise is much smaller, especially from this range to this range, right? So this particular band here has a much smaller noise, and obviously it would make sense that if we have such a channel, then we should use this frequency range, which is here in this band, to communicate or to transmit our signal, because in this frequency band the amount of noise is, or the power of noise is very less. So it's in terms of an analogy, if you were traveling from point A to point B and there are two routes to go from A to B, then it would be wiser and makes more sense to choose the route which has less traffic as compared to the route which has more heavy traffic. So similarly, if we have a communication channel where the noise is more at certain frequency bands and less at some other frequency bands, it would make sense that we transmit at the frequency band which has a lower amount of noise or less power of noise. But unfortunately, that is not the case with white noise. Okay, the noise we come across in communication channels is white, and for white noise, the power spectral density is flat. So therefore, irrespective of which frequency that we are transmitting at, the amount of noise is going to be the same. So white noise is going to be something like this. So whatever frequency we communicate at, we have to have some mechanism to deal with the noise so that the received signal can be recovered as accurately as possible in order to replicate and get back what was transmitted. So what I've shown here in the blue is white noise, and the red one is there's no specific name for it, but we'll just call it as non-white noise, or we can also call it as a colored noise, okay, because it's not white, it is some color. So we'll just say it is colored noise, non-white or colored noise, okay. In practice, however, we don't come across colored noise. What we see is typically white noise, okay. So that's the second attribute, which is white, and the implication of that is that way, irrespective of which frequency band we use for communication, we have to deal with the noise problem. The next attribute of noise that we are interested in, or the noise that we deal with, is the Gaussian noise. So what do we mean by Gaussian? So as we saw earlier from the waveform for the noise signal, we see that the noise signal is a random waveform, and the moment we see randomness anywhere, immediately we have to take the help of the concepts of probability. So we don't know exactly what would be the noise amplitude at any instant of time, but we want to have some probabilities as to which noise amplitudes are more likely to occur and which noise amplitudes are less likely to occur. So we want to know what is the probability that the noise has a certain amplitude, and what is the probability that the noise has some other amplitude, and so on. So the noise that we deal with in communication channels has a Gaussian probability distribution. So the noise has Gaussian distribution. Okay, what do we mean by the Gaussian distribution? The Gaussian distribution is given as P of x is equal to, where x is our variable. Again, to be specific, since we are dealing with the noise signal, I'll write it as P of n. It can be any variable. So since our noise variable is n, so it's P of n is 1 by sigma square root of 2 pi e power minus half n minus mu by sigma the whole square. So that's the probability density function of Gaussian noise, or that's the PDF or the equation for the Gaussian PDF or probability density function. Now n denotes the noise amplitude. What is the probability of the noise amplitude having a value n? And sigma and mu represent the mu is the mean and sigma is the standard deviation. So mu is the mean value and sigma is the standard deviation. Again, these are terms you must be familiar with from your statistics course. Okay, so mu is the mean of the Gaussian distribution and sigma is the standard deviation of the Gaussian distribution. Now, if we plot this PDF, it's going to look something like this. So the Gaussian PDF has a bell-shaped curve, okay, and the tail of the Gaussian PDF, it does not touch the become zero. It goes it becomes smaller and smaller and smaller, and touches and becomes zero only at infinity. Okay, so the tail keeps continuing till minus infinity and plus infinity, and the central value that we have here, that's the mean value. So that's our mean, which we denote as mu. Let me write that mu a bit clearly. So that's our mean value, that's the central value. So what we have on the x-axis is the variable, and on the y-axis is the probability of that variable taking a certain value. Okay, so n is the variable, or the values that that variable can take. So at the center is the mean value of that variable, and on the y-axis what we have is the probability that that particular variable has the particular value on denoted on the x-axis, right? So at this point, that's the probability that the noise has a value equal to mu, and so on. Now, the noise that we are going to deal with, we will say that this is a zero mean Gaussian noise. That means it is centered on zero. So it has some positive values and some negative values, and if you take the average over a sufficiently long period of time, then the positives and the negative samples will cancel out each other, and we will end up with a mean value which is equal to 0. So we could have the noise whose mean is equal to 0. Okay, in general it is any mean value mu, and if it is 0, then this central component here mu, this value, the central component, will be equal to 0 here. Now what is the standard deviation? The standard deviation sigma denotes the spread of the values from the mean value. So if the standard deviation is small, then this bell-shaped curve will be very narrow. If the standard deviation is high, then the bell-shaped curve will be much wider. So let me draw some values. So standard deviation, so let's say that's some standard deviation sigma. Okay, now if we had another distribution with the same mean but with a smaller standard deviation, it would look much narrower like this. So let's say the mean is the same, but it has a smaller standard deviation. So the standard deviation in this case will be this value, which let us call as sigma 2. I'll call the first one as sigma 1, and for the red PDF, the standard deviation, let's call it as sigma 2. And we'll draw another PDF which has the same mean. By same mean we mean that the central value is the same even for the red PDF as well as for the blue PDF. The central value is the same mu, so therefore the mean is the same. Okay, the only difference between this black PDF and the red PDF is the standard deviation. That means since the standard deviation for the red curve, for the red PDF, is smaller, that means all the values are very close to the mean value. For the black PDF, the values are more spread out away from the mean value. And if you had, say, a third distribution whose standard deviation was even bigger, then we could have a PDF which looks much spread out like this. Again, the mean value is the same, but the standard deviation is much wider here. So the standard deviation, say, that's the third standard deviation, which we'll call as sigma 3. Right? So sigma 3 is larger than both sigma 1 and sigma 2. That means the numbers, they have the same mean value, but the distribution of the numbers from the mean value is much more, or the spread from the mean value is much larger in the blue PDF. Okay, so the relationship between the sigmas, so sigma 2 sigma 2 is smaller than sigma 1, which is smaller than sigma 3. Okay, so we have the standard deviations of these PDFs. So basically it's like it's saying, okay, we have a sequence of random numbers, but how far away are they from the mean value? The distribution, how far are the numbers distributed away from the mean value? If the spread is more, then the PDF is wider, as in the blue case. If the spread is less, then the PDF will be much sharper. The smaller the standard deviation, the smaller will be, or the sharper will be the PDF shape. Okay, so that's the implication or meaning of these parameters, the mean and sigma. Now I'll stop here for this lecture, and in the next lecture I'll go into more details of the Gaussian PDF. So we have discussed today all the three attributes of the noise that we are dealing with. The first is that the noise is additive, so that means it gets added to the transmitted signal. The second is that the noise is white, which means that it has equal component, equal mixture or equal proportion of all the frequency components. So we have frequency on the x-axis. At all the frequencies, it has the same amount of noise power. And then we also talked about the Gaussian distribution, which is that the probability distribution of the noise signal follows the Gaussian probability distribution, which is given by this equation. And if you plot this equation for different values of sigma with a fixed mean value, we'll get something like this, where a bigger value of the standard deviation means the PDF is wider, and a smaller value for sigma means the PDF is going to be much narrower. Okay, we'll continue further in the next lecture.